How do these interconnected structural and electrochemical characteristics collectively deepen our understanding of the relationship between cathode architecture, ion transport dynamics, and polarization effects in sodium-ion battery materials, and what further experimental investigations could be pursued to optimize these parameters for the development of next-generation energy storage systems? How does the comparison of the charge and discharge curves for Na2Fe-PO4F and Na2Fe/2Mn/2PO4F reveal the underlying differences in their electrochemical behavior and ion transport dynamics, and what do the specific features such as voltage plateaus, slope variations, and potential hysteresis indicate about the respective mechanisms of sodium intercalation and deintercalation in these materials? Can Davis-Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what ways might the incorporation of manganese to form the mixed metal compound influence the structural and electronic properties compared to the pure iron-based material? And how can these modifications be directly correlated with observed changes in the shape and stability of the voltage curves? How do the distinct voltage platforms observed during cycling reflect the efficiency of the redox reactions involving the phase-2/phase-3 couple? And what additional insights can be drawn from the differences between the charge/discharge profiles regarding the occurrence of phase transitions, material polarization, or internal resistance effects? How might the analysis of these electrochemical curves serve to validate theoretical predictions about the diffusion pathways and kinetic properties within the layered structures? And what further experimental techniques such as impedance spectroscopy or cyclic voltammetry could be employed to deepen our understanding of these processes? In what ways do the observed characteristics of the charge/discharge curves inform us about long-term cycling stability and capacity retention in these sodium-ion battery cathodes? And how could this information be used to guide future modifications or optimizations in material design to enhance overall performance? How do all these interconnected questions contribute to a more comprehensive exploration of how compositional engineering, such as the partial substitution of Fe with Mn, impacts the complex interplay between crystal structure, redox activity, and sodium-ion mobility as reflected in the charge and discharge behavior of these innovative cathode materials? How does the crystal structure of Na2Fe-PO4F, as shown in diagram A and represented by its charge/discharge curves in figure C, compare to that of Na2Fe/2Mn/2PO4F, whose structure is depicted in diagram B, with its performance presented in figure D, and what specific features in each structure, such as the arrangement and connectivity of polyhedral units, might influence sodium-ion mobility within the layered framework? What?